Today's topic is going to be on crystallography. Crystallography is the science of determining the arrangements of the atoms in a crystalline solid. So what we want to do is we really want to look at how are we going to describe this crystal. And remember, a crystal is something that's uniform in each direction. Crystals are very easy to be able to discuss and to know what's going on because they're in a very regular pattern. And if they're in a very regular pattern, and if we know what directions that pattern follows and goes out in, then what we can do is we can really know what's happening throughout the entire material. And if we know what's happening throughout the entire material, it means that we know how it's bonded together. It means that we know how the electrons are going to move. It means that we know a lot about what's happening. And so what we want to do is we want to look at three things. Within a crystal or in a unit cell, we can look at the position of the atoms, so where the atoms are within 3 dimensions in space. We can look at the direction that the atoms line up, nearest neighbors, second nearest neighbors, and such. And then we can look at planes of atoms, and we can see how those atoms stack up and how they spread out in 2 dimensions, and those 2-dimensional planes are stacked to make a 3-dimensional crystal. To be able to talk about this in an easy way, if you're going to be reading papers, if you're going to be writing papers, if you want to discuss these things, we want some consistency. And so one key point, and what we're really going to discuss for a lot of this video, is notation. And so we need to know how to write and how to discuss these things. The first one that we're going to talk about is position. And what we're looking for is where the atoms are in the unit cell. So the first thing that we really have to understand is the origin of a unit cell, the origin of a crystal. If we're talking about something being in 3 dimensions in space, we need to understand that the origin is trivial. It really doesn't matter where we call something its origin, and that is really helpful, especially once we understand or remember that a crystal is the same over and over and over, that it repeats, because it doesn't matter which one we start with, because, well, if we start with 1, we're just going to keep moving in each direction a certain number of ways. And if I decided to even rotate the crystal or start at a different particular atom, it really doesn't matter because it's the same everywhere. So we don't really need to know a true origin, and in reality there isn't a true origin. So what we're going to do is we're just going to pick a spot, we're going to pick an atom, and we're going to say this, for us, is going to be the origin. For the convenience, normally the back corner, the bottom left-hand corner of the unit cell when you're looking at it, is often picked, and that's what I'm going to be using today. When we finally do decide to write out our position, what we're going to do is we're going to make sure that we have no enclosures. That's going to be talking about different types of parentheses or brackets. We're not going to use any brackets. Writing fractions are going to be perfectly okay. I can use negative signs, those are okay. And I'm going to be able to use commas. And right now, without really going into anything, you might be a little trying to figure out what am I talking about. So let's do an example. So first thing I'm going to do is I'm going to draw a coordinate system where we have X, Y, and Z. The next thing I'm going to do is on this coordinate system, I'm going to draw a unit cell. I'm going to draw it with dotted lines. And so hopefully you can tell from my drawing that I have this cube here. So this is going to be for a cubic system. So either a simple cubic, a body-centered cubic, or a face-centered cubic. So one of our cubic Bravais lattices. And we're going to go ahead and call the origin this point here. Whoopsies. All right, there we go. All right, so our origin is going to be right here. I'm going to go ahead and call that O for origin. I'm going to put 2 points on here. I'm going to put a red point right here, and this is meant to be on this dotted line, so it's going to be on this edge. And I'm going to call this point B. And just so we have a second one so that we can do this more than once, I'm going to put another one right here on this corner. And I'm going to call that point A. What I want to do is I want to know what the position is for each one of these. So first, let's just start with the origin. That one's nice and easy. If I were to write this in math class, I would say that this origin is at point 0, 0, 0, and I would put it in parentheses. And that's what you would say the point is in 3 space if you were in math. We're going to do that slightly different here. We're going to go ahead and do a very similar thing, but we're going to use our rules here. No enclosures. The enclosures would be the parentheses. So I can write that, what I did previously, but we're not going to put it in parentheses. If I need to, I can use fractions. Negative signs are okay, so I'm allowed to use a negative sign if I have to go backwards, and I separate them with commas. And so with all that, my origin would again be 0, 0, 0. So pretty straightforward. I'm going to go ahead and do A next. So there's A. And what I'm going to do is I'm going to do again X, Y, and Z. I'm going to separate them with commas, but I'm again not going to put parentheses around them. And so in my X direction, I don't come any direction in X. I go 1 in Y, and I'm going to go 1 in Z. And so the position of A would be 0, 1, 1. We'll do B real quick, and then we'll discuss. I have B. B, what I've done is if we start at the origin here, we move 1 unit in the X direction. So I have 1, comma. In the Y direction, we don't move anything. We just stay right here. So 0. And in the Z direction, I go halfway up. So I'm going to go ahead and write 1/2. And this is how you write the position of atoms in a crystal. Now, we got to remember that the origin doesn't matter. Really, the orientation doesn't matter, because who can really tell if a crystal is upside down, which side's forward, which side backwards, which side's up, which side's down, which side's left, which side's right, if it has symmetry in all directions. If it is a perfect crystal, it looks the same no matter which way we turn. And so possibly, depending on how this was set up, some of these might have been negative, some of them might have been in different orders. Possibly A, if we would have had our X, Y, and our Z's changed up a bit, our point A could have been written as 1, 0, 1 or 1, 1, 0. Depending on where we pick our origin, it could have been negative 1, 0, 1. And so there are some variants here. Remember, all we did though was we picked a very specific origin. We got to pick it, and we did that. And then we decided basically where other atoms are with respect to where we decided to pick our origin. The next thing would be direction. And what we mean by direction is what is the relative direction between atoms in the unit cell or within a crystal. What we want to do is we want to move the coordinate axes so that the line or vector passes through the origin. It makes it very easy to be able to describe things if we are using the origin. And we want to define the vector from the origin to a specific point. Again, just some things here when we actually finally start to write down our things. This time we are going to use enclosures. We're going to use brackets, and brackets are going to be the square brackets here. We're not allowed to use fractions here, so what we're going to do is we're going to make sure that we have the smallest set of integers that are going to be used. We're not going to be using negative signs. If we do have to go backwards, we're going to bar a negative value if we happen to do that. And I know up here I said that we want to define the vector from the origin to a point. We could go from a point to an origin and possibly be going backwards at that point. We'll do that in one of our examples so that we do get a negative number. We're not going to use commas here. Instead, we're just going to make sure that there's a space, and that space is going to be used as a separator. So I'm going to go ahead and I'm going to draw a coordinate system again. We're going to do our x, y, and our z. I'm going to put a unit cell on here. Here's our x, here's our y, our z. We'll put a cubic system unit cell in here, and that's just going to help us to be able to visualize what's happening so that we can see. And what we're going to do is we're going to use the exact same points as we did for our last one. I have my origin here. I'm going to have A up here, and I'm going to put my B on this side, and we're going to go ahead and figure out what we'll do just to, so we have a negative number here. I'm going to actually say let's start at A and go back to the origin. So if I say that we're starting at A and going back to the origin, what I have is I want to be able to describe this vector. I mentioned that what we want to do is we're going to end up using square brackets. We're not allowed to use fractions, so we're going to use our smallest set of integers that are possible. There's no negative signs, so we're going to bar for negatives. We're not going to use commas. Well, first, let's just kind of take this a little bit slow. If I start here at A, what am I going to be doing to get to my origin in my x? And in my x, I don't go any direction because this point is in the YZ plane. In the y direction, I go -1. And in the z direction, I'm going to go -1. And so I start off with saying, all right, well, I have this 0, this -1, and -1. And of course, you should start freaking out right now because I use negative signs, I have commas, I don't even have square brackets. What I'm doing right now is I'm just writing out, I'm practicing, I'm writing out what I know. So what I'm going to do is I'm going to say, all right, well, I know this. I need to take away my commas, and I need to take away my negative signs. So if I take away my commas, I end up with 0, 1, 1. And to take away my negative signs, I said I need to bar my negative values. And what that means is we're going to just put a line over the top of these. And that's telling me that that value is going the opposite direction. It's not 1 in what we traditionally call the positive direction. It is 1 in the opposite direction. We just don't use a negative sign here. Last thing I'm going to do is I'm going to go ahead and put these in square brackets. And so this first one here is incorrect. I just wrote that down to be able to get some things on paper, but I went and I transformed that into 0, 1 bar, 1 bar, no commas, and I have my square brackets. Go ahead and we'll do B. This time we will start at the origin, and we'll go to B. And so if I go from my origin to B, and again, I'm just going to write down a few notes here. First thing I'm going to do is I'm going to say, all right, to get to B, I have to go 1 in the x direction. In the y direction, I go 0. And in the z direction, I go 1/2. Now at this point, I don't have any negatives that I have to deal with, but I do have this fraction. And I want to clear the fraction. All right, to clear the fraction, I want to turn that into an integer. The way I'm going to do that is I'm going to multiply this entire thing by 2. Because if I multiply the entire thing by 2, I shouldn't have a fraction anymore. I multiply the whole thing by 2, I get 2, I get 0, and I get 1. I'm going to make sure that I don't put my commas in here. And I'm going to go ahead and put my square brackets in. And I have a direction of 2, 0, 1. And that is all that I have to do my directions. There is a couple things that we might want to talk about here, so we'll go ahead and do it. Remember, since this unit cell is identical if rotated, and this origin that we picked is completely arbitrary, then there are going to be multiple directions that are going to be virtually similar. They're going to be identical. Take B, for instance, here. Going from the origin to B, what we've done is we've gone from one point and we've gone in one direction. It doesn't necessarily even have to be the x direction. In a particular direction, we have gone 2 forward for every 0 that we've gone in a second direction, and 1 in that third direction. So it really doesn't matter which one we pick. I could say I'm going to be going, let me use, let's see, we'll use green here. I could say, well, what if we went this direction? Or what if we went this direction? They're all going to be identical because remember, there's symmetry in this crystal, and so it doesn't matter which one we're talking about. Because of that, what we want to do is we want to talk about a family of directions. And what a family of directions is it means that we're not concerned with a very, very specific orientation of a crystal. We're not concerned with which way we're calling X, Y, and Z, because we understand that there's plenty of symmetry. So instead, what we're going to do is we're going to write it out as a family. And to write it out as a family, what we're going to do is we're going to use the exact same basic notation rules as we did for our direction, except for we're not allowed to have negatives now. And the reason we're not allowed to have negatives is because just like A here, I could have flipped the arrow into the other direction. I could have had it going from the origin to A, and that's the exact same vector. And if I were to do that, there would be no negatives. And so there's no reason to have a negative when I'm just talking about a arbitrary direction. To let people who look at this know that I'm talking about a family of directions instead of a very, very specific direction, I'm going to use these greater than or less than signs. I'm going to use these caret signs, sideways carets, as my enclosures instead of the square brackets. And people tend to write these in order from smallest to largest, just to keep it a little bit neat and clean. So if we're going to go ahead and we're going to turn this A to origin, A to O, if we're going to turn that into a family, what we would do is we'd say, all right, we're going to order it from smallest to largest. It was already that way. So my A to O, 0, 1, 1. I'm going to make sure there are no negatives or bars, so I didn't add those here. And all I'm going to do is I'm going to change my square brackets to these enclosures here. And that's all I'm going to do. And what this really means is it says anything, and it really doesn't matter what direction we're looking at, what orientate. Okay, let me take that back. The direction is important. That's what we're discussing here. It doesn't matter the orientation or the coordinate system that I decide to choose. This 0, 1, 1 direction, really what it comes down to, it is a face diagonal. Think of this as a cube. Maybe if you had dice or something, I would draw a line from one corner to the other corner on a face, and every single one of those would be a 0, 1, 1 direction. Now, if we wanted to be specific, we could say, well, depending on the orientation of the dice at any given time, maybe one of them is going backwards and we have a negative. But with the family, we don't care because we're saying we can look at the dice from any direction, and a 0, 1, 1 direction is just going to be a face diagonal. And that's all a 0, 1, 1 is a face diagonal. All right, let's do this last one here, this origin to point B, O to B. I'm going to order my values from smallest to largest, and so I'm going to go 0, 1, 2. I'm going to make sure there's no negatives. There weren't any negatives to begin with. And then I'm going to change my square brackets to my carets here. And that's it. That's how I turn a specific direction into a family of directions. We'll talk more about why we do this and what this means in class. I did want to mention really quick, and again, this is for cubic systems here. If I want a body diagonal, and a body diagonal is a 1, 1, 1. If we go back here, a body diagonal would start at the origin and it would go completely opposite. It would go through the entire body. But I have other possible places I could have a body diagonal. I could start here on my, I'll put a box. I could put one there, and it could go over one, up one, and out one. If I were to connect these two boxes here, I would have another body diagonal. And if I took, and I have an X at this point, and I go down one, over one, and out one, and put another X here. If I were to connect those two, I would have another body diagonal. It just goes from one corner to the furthest other corner of my cube. The family of directions would just be called a 1, 1, 1. It goes in one direction, one more in another, one more in the last direction. That would be the family. The specific direction, depending on which one I'm looking at, possibly we'd be talking about negative signs, but the family doesn't care about negative signs. What's important here is these three things here. If I want to look at a cube edge, and let me draw a cube really quick. We'll draw a dotted line cube. All right, so here is my cube. I'm going to go ahead and write my cube edges. My 0, 0, 1 is going to be in red, so I'll go ahead and underline that here. That would be something like this. It's an edge right along there. I go 0 in one direction, 0 in another, and I go 1 length in the last direction. It could be anywhere, though. It could be maybe the first one is a 1, then a 0, 0, if I was looking at something specific. A face diagonal we've talked about. I'll go ahead and do that in blue. A face diagonal would be something where I go from this face here, this square that's on a surface, and I go from one corner to another corner, and that's my face diagonal. And lastly, I have, we'll go from this point to this point here. The body diagonal goes throughout the entire three-dimensional structure, and that is my body diagonal. What we want to look at here is we want to try to find the most dense direction. That's one of the things that we want to do. If we can find the most dense direction, what we've found is we've found our nearest neighbors. And depending on if we have our cube, which is a 0, 0, 1, or a face diagonal, which is 0, 1, 1, or a body diagonal, which is 1, 1, 1, those are all going to be our most dense direction for certain types of Bravais lattices. The cube, if I draw this picture, remember last class, or last video and last class, we drew our simple cubic structure. And it looks something like this, where these were touching on the edge, and we were looking for our packing densities. So hopefully we're going to start tying some of this stuff together. And we said that we had this length A on the side, and this length A was 2 radiuses. A equals 2 radiuses. Well, the reason why we know that, and the reason why we care, and one way to discuss this is that is going to be our cube edge. So for simple cubic, our most dense direction is going to be our 0, 0, 1. This is our dense direction for our simple cubic. We can go look back in your notes, see if you can see that one. I'm not going to do this for my face diagonal and my body diagonal. I will tell you one thing. One of these, the face diagonal, is going to be the most dense direction for either the body-centered cubic or the face-centered cubic. And this body diagonal of 1, 1, 1 will be the other one. It will be the most dense direction for the either the face-centered cubic or the body-centered cubic. But I want you to go back and I want you to think about it. It's something that we can discuss in class after you've had a chance to look at it yourself. Next up, we're going to look at planes. Really what a crystal is, it's a three-dimensional thing, and so we could think of that three-dimensional thing as nothing more than we have a plane of atoms, and then we put another plane of atoms directly on top of it, and we keep stacking these planes up until we have a three-dimensional structure. Think about it if you were stacking something, let's say that you were working at a grocery store, you were stacking up the oranges. You'd have to first put one layer down, you'd stack them up, and then you would have to put another layer down, another layer down, another layer down, and eventually you'd have a nice three-dimensional stack of these oranges. And that's what we're going to do here. To do it, what we're going to do is we're going to use our Miller indices. Miller indices are our H, K's, and L's of our equation in space. Now, there's a couple ways we can write this equation. Both of these here are ways to write an equation. What we're going to do is we're going to let H equal 1 over A, K equal 1 over B, and L equal 1 over C. And our A, B's, and C's here are going to be our intercepts with our X, Y, and Z axis. So what we end up with this equation, Hx plus Ky plus Lz equals 1. Now this is going to have actually the most steps out of all of them. First thing we need to do is we need to make sure that we find the inverse or the reciprocal of the axis intercepts. And we can kind of see that from the equation up here. We have this equation that uses the inverse of our intercepts with our X, Y, and Z axes. If we're going to define this plane with H, K, and L, then we can see that we're going to need to take those reciprocals at some point. A couple rules that we're going to do. We're not allowed to use fractions. They have to be whole number integers. No negative signs again, so if something comes out negative, we're just going to bar that number instead. We're going to put a little bar above it. Again, no commas, and this time we're going to use actual parentheses. A side note is we can't let our plane go through the origin. And I'll show why in an example right here. One other thing that I wanted to mention is there's a very useful property where our plane, as described with H, K, and L, is going to be perpendicular to our direction with those same H, K's, and L's. So if I can figure out one, I can figure out the other relatively easily. So we'll talk more about that in class. If I remember in this video when we draw our plane, I'll show that as well. So let's say that I have a plane, and this plane, first I'll draw in my unit cell. All right, so there's my unit cell on my axes, and I'm going to draw on a plane. And what I'm going to do is I'm going to say our plane is going to cut through the middle of this. And so here is our plane. It goes diagonally through the center. I sometimes think of this as if I make myself a big sandwich and I cut it diagonally into triangles. That's basically what I've done here. I've taken this cube, I've cut it diagonally. And what I want to do is I want to figure out what's happening. Now the first thing that I should do is I should figure out where are my axes intercepts. And so if we do that, I would say, well, I have an axis intercept. It intercepts my x-axis at 0, it goes through my origin here. So my x-axis, it would go through 0. These are my intercepts that I'm finding. It goes through my y-axis, again at 0. And it goes through my z, L everywhere. So this is going to be infinity. And this is going to be a problem because the first thing that we're asked to do is we're asked to find the inverse or the reciprocal of our intercepts. Infinity, I guess you could flip around and say, you know, that's 0. But then I have this, if that's true, if I take 0 and invert it, then this becomes infinity and this becomes infinity here. And that is something that you can't put into an equation. I can't use that as an HKL in this equation. So I can't use it if I go through the origin here. If I go through the origin, then I get some zeros and things fall apart. So one of the things that you have to do is if your plane goes through the origin, you're going to have to figure out how to move the plane or move the origin, one of the two. And remember, we can do that perfectly fine because the origin was completely arbitrary in the first place. And so what I could do is I could say I want to find a new origin, and you can really pick whatever you want. I like to pick something somewhat simple. Maybe I'd move the origin to right here. And so our new axes would be here. My x-axis would be the same. And I would have my new y-axis here. I could then very well figure out where my intercepts are. I'm going to redraw down here, kind of with that shift. And to do that, what I'm going to do is I'm actually going to draw my unit cell behind this coordinate system. Because I moved my origin. My new origin, and I'll draw it in blue this time. This is my new origin right here. I still have the same plane. So my plane is right here. But we can see that our plane doesn't go through our origin, so this should work just fine. So the first thing I'm going to do is I'm going to figure out my intercepts. My x, my y, and my z. And in this case, my x, well, if this is my origin and x is positive coming out of the screen, then it's actually going to be a -1 where it's intercepting the x-axis. My y-axis is here, so it is intercepting at y equals 1. And in this case, z, my z intercept, it never quite gets there. This is basically an asymptote here. We could say it's getting close. It's not necessarily leaning up against it, but we'd have to go really, really far out. This is perfectly parallel. It would never touch it, but we could say that the intercept, because it never will touch it, we could say that the intercept is infinity. What I'm going to do is I'm going to take the inverse. And take the inverse of these. The inverse of -1 is -1. The inverse of 1 is 1. And we're going to say that the inverse of infinity is 0. Now the next rule is we can't have any fractions. In this case, we don't. And so we're perfectly okay just to move on. And we have our steps right here. Let me actually scroll up so we can talk about this. First, we identify the x, y, z intercepts. If the plane passes through the origin, we move it, which we did. If there's no intercept, we call it infinity. We did that with z here. Took the reciprocals or the inverse. We made sure there were no fractions, and then we use a parentheses with no commas. And so our plane would be bar 1, 1, 0 in parentheses. Now we'll talk really quick about a family of planes. Just like with everything else, this is a very, very specific one drawn through here. Let me draw another one. It's going to get a little crazy if I draw another one in here, but there are other places where I could draw this exact same plane. I could cut my cube this way. And again, what I've done is I've taken my cube, I've cut it diagonally, and that is, in essence, the exact same plane. It would be written slightly different. My negatives would be somewhere else. My 0 might be in a different position, but it's essentially the same plane, and the only reason it would be any different is because I arbitrarily chose a coordinate system and an origin. So we have a way of writing, again, planes, a family of planes. We're going to take a plane direction, or sorry, a plane that we've come up with. And what we're going to do is we're going to just change a couple things. Number one, we're going to use braces, curly brackets, sometimes they're called, instead of parentheses. Again, we're not going to include any of our negatives or bars. We're just going to make sure everything is just a whole number. And then we're going to order from smallest to largest. So in this case, I would order from smallest to largest, so it would go 0, 1, 1. I would make sure not to put my bar on either of those ones, and I would put my curly brackets on there. And that's all you have to do to say that this is a family of planes. One of the key things that we're really looking for and why we care about this, yes, it seems like a lot of notation. It seems like you're just kind of writing some things out. We can talk about, we can describe the crystal with these things, but the real reason that we care to describe the crystal this way is because these planes and directions, they're going to mean something to us. So in this case, let's talk about our close packed planes. We're not just looking to pick some random plane somewhere. What we're really looking for is we're looking for planes of atoms that are as closely packed as possible in a certain in a certain plane. We want to see where they are the most dense. I have 3 unit cells here and 3 cubes here, which I'm going to draw in my hard spheres. This first one that we're going to do is going to be for simple cubic. SC, simple cubic. For simple cubic, I have an atom on each corner. And that's it. And what we want to do is we want to see which plane in here is the most dense, the one that's most closely packed. It can sometimes be a little bit hard to tell if we're just looking at a picture like this, kind of this wireframe just with dots where the center of the atoms would be. What we're going to do is we're going to try to visualize this as a cube that has hard spheres inside of it, hard spheres of atoms. And so we're going to do that by drawing in our atoms here. Something along these lines. So I have kind of these, and this is just the cut of this cube if I were to stack atoms like this. It's important to note that these atoms touch where they can, and so in the case of simple cubic, they're going to touch right here on this edge, and this edge has a length of A. What we want to do is we want to try to figure out what would be the best plane, the best place to cut this, so that we can get the most densely packed thing. If I were to cut this directly in half, cut it right through here, and then I opened it up and kind of saw what the inside looks like when I cut it, it would basically be nothing but empty space. We didn't cut through any atoms. So that's not a good place to cut if we're looking to find the most densely packed plane that we have. What we're going to do in this case is we actually are going to find any one of the surfaces. So here's a complete surface here that corresponds to this surface. And in the case of a simple cubic, this is actually going to be the most densely packed plane that we have. So we could draw that off to the side, and I could say if I just wanted to draw the cross-sectional plane that is most densely packed, it would look something like this, where these are my atoms, and then I have my empty space in the middle. And if I wanted to, I could relatively easily figure out in this plane, the most densely packed plane, how much atom do I have compared to entire area. So that's simple cubic. Body-centered cubic gets a little bit more involved. So body-centered cubic, I have my atoms on every corner, just like with simple cubic. But then what we do is there is one wedged in the middle here. And this one in the middle, sometimes it's hard to see. I'm going to put dotted lines in. Maybe that'll make it easier to see what's happening. It's kind of right there sitting in the middle. It's not on any surface. It's dead center in the volume of this unit cell. I'm going to draw a hard sphere version of this, which is difficult because you can't really draw the inside very well. It's very difficult. But one thing I can tell you, if you try to put a simple cubic cell together and then you try to wedge an atom in the middle of it, it's going to stretch out that simple cubic structure. And so as I draw this simple cubic structure, these are no longer touching on the edge, my atoms. They're not touching on the edge because I have somewhere in the middle, and again, I'm not an artist, so I apologize. Hopefully you can visualize this. Somewhere in the middle of this, I have an atom that is pushing all those things apart. It's stretching those that simple cubic structure. So what we want to do now is we want to try to figure out what plane is the most densely packed, the close packed plane. Well, the most closely packed plane for, and this is body-centered cubic, is going to be a diagonal cut. That's the same one that we did up here for our example of the plane and family of planes. It's a diagonal cut. That is the dense plane for bodied center cubic. This over here is still A, but this A no longer is my two radiuses. There's this gap here. And so you kind of got to be able to figure out, okay, well, how could I relate my radius to my A? And what you'd have to do is you would have to figure out which atoms are touching. In this hard sphere picture, we always have to have spheres that are touching. And so what we would do is we'd actually have to make this cut, and we would open up this cube, and we'd look at the surface of this cut. We wanted to see this cross-sectional area. When we do this, we'd actually get a rectangle. And the reason for the fact we'd get a rectangle is because the height of this cut is A, but the length isn't. The length is actually the diagonal of this square on the top. And so I'd have a length A on the side. I'd have something else for the height is A, the length would be something else. And what I would do is I would draw this in here. I can see that from the sides. I can see that these atoms aren't touching, so I've left a gap. But on the inside, and again, my drawing's going to be horrible here. I do have atoms touching. And the reason that they're touching is, again, I wedged this atom in the middle, and it pushed these corner atoms out a little bit. And to keep them pushed out, it's contacting all of these corner atoms. And so what I could do is I could say, yes, I do have complete contact throughout the material that goes through right here. This is going to be, so I'll draw it here again. If I cut right along here, that is going to be my plane that is most densely packed for a body-centered cubic crystal. Lastly, we're going to have face-centered. Face-centered again starts out with a simple cubic crystal structure. But what we're going to do this time is we're going to put an atom on every single face. There's 6 faces. I'm going to put one on this top face here. I'm going to put one on the side face. I'm going to put one on the bottom. I'm going to put one on the other side. On this face that's kind of coming out towards the screen, I'm going to put one here. And the one that's going into the screen, I'm going to put one here. Sometimes I will put little dotted lines. We'll see how that looks. Like for this top one, to kind of see that it's sitting right in the middle, maybe I'll put a dotted line there. The one on the side here, I could say, see that one's sitting right there on the side. But if you do this to too many of them, you can see it just kind of makes a mess. And so I'm going to take some of those out for now, so they don't have to see all of those. I'll leave a couple of them in. Might make it a little bit easier to see. All right, this one again is for the face-centered cubic, or FCC. And I'm going to draw in my hard spheres. I'm actually going to start with the center one because that is going to sit right there, right there, right there. Those are the ones that are sitting on the face, on each face. And again, those ones that are sitting on the face are going to be stretching out. Oh, that's really bad. They're going to be stretching out the simple cubic structure that we previously had. So that is a horrible drawing. Hopefully you can tell from that one though, I have an atom on every face, and those atoms are stretching out our simple cubic structure. They're pushing them out. What we're going to do here is we're going to draw in our most densely packed plane, which is going to be actually it's going to look like a triangle through here. That is going to be my most densely packed plane. I'm going to go from one corner. I'm going to go to another corner, to another corner. I'm going to slice it through diagonally. So when I'm done, I would kind of have these two pyramids. And if I open that up, I'm actually going to get a triangle. There's my triangle. It's going to be more, it should be like an equilateral. I'm going to have an atom at every corner, right? Because that's what I see here. I see an atom at this corner. I see an atom at this corner, an atom at this corner. As we cut through this, you'll see that we go directly through the center of an atom right here on every single cut. On the side of this triangle, we go directly through an atom. And so we'd end up with something kind of like that, but not. These atoms are going to all touch, something like that. Maybe we'll take a picture, maybe we'll take a look at some pictures later so you don't have to see my horrible drawings of this. But this is going to be the most densely packed plane. And you can see that it's actually very, very densely packed. You could take you could do some math, use a little bit of geometry to figure out exactly what the density of this plane is. But this here is my most densely packed plane. We decided earlier, or found out earlier, that the FCC is the most densely packed cell. This is actually also the most densely packed plane out of these three as well. Now, the reason we care about this is because the material tends to like to keep together. These bonds don't like to break if they don't have to, right? A material likes to stay together unless it can't anymore. Once enough force is applied, some bonds are going to break, but the direction that these planes that are very, very tightly bound together are going to be the planes that they're going to slide. They're not necessarily going to break apart. So we'll talk a little bit about how planes slide and move probably in the next few videos. But for now, it's important to know that for every single Bragg lattice, and we just chose 3 of them here. We chose the simple ones to draw. But for every single Bragg lattice, we could draw in planes. And some of those planes are going to be close packed. Means that it's the most close packed that we can get out of that structure. If I wanted to, I could draw a 0, 1, 1 plane here in my simple cubic. And remember that 0, 1, 1 is what we did in this example here. I could have a 1, 1, 1 plane that I could draw through my simple cubic. That's the one that looks like a triangle. But again, that's not necessarily going to be close packed. But it could be a good practice to go through and draw it and try to figure out what it looks like, trying to visualize those things. So once we can figure out these planes, something else that's going to be very important is we want to figure out what the shortest distance between any families of planes could be. We want to see how these atoms are stacked on top of each other in 3 dimensions. So if I put a plane of atoms down and I put another plane on top of them, my question is, how far apart are those planes? And we can see that, or we can calculate that with this equation here. I sketched this off to the side. Just a simple 1, 1, 1 plane. If I had, and of course if it's a crystal, it's not an if, we do have another unit cell off to the side here. I could draw another plane. Looks identical. It's just the next unit cell over is going to have a plane that looks like this. And I'd have another one behind it, and another one behind that, and another one in front of that, and one above it, and one below it. Right? These planes stretch out in all directions. But what this D is really looking at is it's saying, what's the shortest distance between this red plane and this green plane? And so the shortest distance, and this is going to be really hard to see, number one, I drew it kind of small, but if I took a point, let's say right here on this plane, and I drew it perpendicular to this red plane, let's say it would end on my blue plane, my green plane right around here. Again, these are perpendicular. I could draw my little perpendicular lines on here, but it's kind of small. But that's what we're looking at here when we say, what's our interplanar spacing? What's the spacing distance between 2 planes? Here's our equation. Remember, A is our lattice constant. That is the length between the length of our unit cell. I forgot to write it on this one. I still have an A here. I need my H, K's, and L's. I need to know what plane we're looking at, and so there you just plug in for this plane right here, this FCC. This is a 1, 1, 1 plane, and so I just put a 1 in for H, a 1 in for K, and a 1 in for L. I do that calculation, and I get my spacing between those. So what can we do? We can actually use X-rays to characterize and measure certain things. We can model these atoms, these planes of atoms, especially as a mirror. We can apply the constructive, destructive interference with them. And what that means is rays that are in phase are going to add up together, and those that are out of phase are going to they're going to subtract each other. They're going to dampen the signal. So let's say that I have an X-ray. I have X-ray 1 that has a wavelength that looks something like this. And I have X-ray 2 that the wavelengths match up. The peaks match up with the peaks, the troughs match up with the troughs. When I do 1 plus 2, when I combine these two waves together, the peaks magnify and the valleys magnify, and you end up with something that looks like that. This is what we call constructive or in phase. That's this one here. That's the blue one, and we see that it amplifies. If I have wave 3 and 4, and they're out of phase, when I add them together, well, I have a large number here and I have a small number here, a negative number. So that's going to basically add to 0. And here I have a negative number and a positive number. That's going to add to 0. I have a 0 here and a 0 here. That's going to add to 0. And so what you end up with is you end up with something that when they combine, they dampen or they are destructive together. So the red ones are dampened. They are out of phase rays. And so we can use this to do something. So here's one method to do things. We use in phase monochromatic incident radiation. That means single wavelength. And we're going to shoot these wavelengths. We're going to beam them. We're going to, whatever you do with the wavelength here, onto a crystal. So here is my crystal plane. And because it's a material, there is a crystal plane below it. And there's a crystal plane below that, and a crystal plane below that, because that's what we do with crystals. I have this wavelength, and this wavelength is coming in. And there are going to be lots of these wavelengths. There's going to be lots of rays coming in. And they're going to come in sync. They're in phase when they come in. This first one's going to come in. It's going to hit this top atom, and it's going to bounce out. And then I'm going to have a second one that comes in, and it's going to hit maybe the second. Maybe it'll make it through the first layer, but it will maybe bounce off the second layer, and it will come out. What we want to do is we want to see after the wavelengths come out, are they still in phase? If they're still in phase, we're going to get, our detector is going to go off because we're going to get this spike in intensity because we have a big wavelength here and a big wavelength here, and when they come together, we get a large wavelength. So it's going to notice that there's something important happening there. And if they're not in sync, then these two are going to cancel out and we're going to get nothing. We could do some geometry here. I'm not going to draw everything in. I'm going to tell you where you could look for this. Maybe in class I'll give you some additional pictures, other things to look at. But because we're saying that this reflects like a mirror, we know that my angle on this side, my incident angle, is the same as my reflected angle. And that's going to be the same for this one down here. We can also, if we're very, very careful, I'm actually going to draw this a little bit larger off to the side, just this part right here. All right, so if I have that coming in and that there, if I were to draw a dotted line down here, and if I were just to take this part out and this part out, this line here, I'm going to call this ray A and ray B. Those have the exact same length. right? Because they're cut off perpendicular right here. So A and B have the same length, which means A prime and B prime, the reflection, they have the same length to the detector over here. And so that means that they're going to be in phase, because if they have the same length, then they're going to be in phase together. And so what we're looking at here is kind of what I scribbled out right here. This length here and this length here. Those have to be a very, very specific length for this to be in phase when it hits the detector. B is obviously going to have to travel further than A. The question is how much further. And if this extra distance that I've kind of scribbled out along here, if that distance is some integer wavelength, then it's going to be back in phase by the time it reaches the detector. All right, so here I have that ray 2, instead of A and B, I guess I had ray 1 and ray 2 here. But the second ray, so in our case ray B, has to travel the same distance as the first ray, but it's going to have something added in. If I wanted to, I could say that this is point A right here. Let me get a different color since I've kind of scribbled that all up. Go ahead and I'll get red. So this is point A, this is point B, and this is point C. So the second ray needs to have traveled the exact same distance as my first, plus the length A to B and B to C. So if this is going to be in phase after the reflection, AB plus BC has to be some wavelength times some integer for that to stay in sync. If we wanted to keep things simple, we could use n equals 1. When we do that, we could simplify things a bit here. But what we do is we say, we don't know if n is going to equal 1. And so what we have is we come up, what we do is we use Bragg's law. Bragg came up with this. There are actually two Braggs, a father-son team who came up with this. And this is the equation to be able to see what's going on, be able to figure out this spacing between planes of atoms. And so we see that we have this D HKL, and we come all the way back up here. Remember, we had D HKL up here. We could do substitutions. We could put things in. We could do a lot with this equation. But this is kind of the basics of what's happening. We'll talk more about it in class. We'll draw some pictures. We'll play around with it. We'll do some practice problems probably as well. But what this does is it gives us a fingerprint of the crystal structure. It tells us, let's say, whether it's body-centered cubic or face-centered cubic. There's what we call selection rules. And so if we want to know something about our material, something about our HKLs, then we could go and we could figure stuff out. And what can we figure out? Well, if my H squared plus K squared plus L squared equals 1, that means that I have something in the form of a 1, 0, 0. And so I have a simple cubic plane. You'll see that simple cubic basically has all of these combinations. Body-centered cubic has peaks when we run this experiment. When we shoot X-rays at a crystal in this manner, we're going to get peaks of intensity at particular planes or at particular angles. And for body-centered cubic, it is when H plus K plus L is even. So in this case, we have 1 plus 1 plus 0, that's even. We have 2 plus 0 plus 0, that's even. 2 plus 1 plus 1, 2 plus 2, 3 plus 1. All of those are even, and if we get an even number, we know that that is body-centered cubic. For face-centered cubic, H plus K plus L is all going to be odd, or it's all going to be even. That shouldn't be pluses, sorry. That should be H, K, and L are all going to be odd, or they're all going to be even. In this case, I have all ones. All of those are odd, which means it's face-centered cubic. We're going to count 0 as even here. So in the case of a 2, 0, 0, all of those are even. My H is even, my K is even, my L is even. We're going to say that that's face-centered cubic. And so we can go through and we can say in any of these cases, so a 2, 2, 2. Number 1, H plus K plus L is even, so it is body-centered cubic. All of these are even, so it's face-centered cubic. And you can kind of go around, you can play around with these. Now you might say right now, this seems like a lot of information. When am I ever going to use this? There are times crystallography is a huge field. We learn a lot about crystals and we can do a lot with them. As of right now, what are you going to use with them? Not a whole lot, except for just some things in this class. If you never end up using these again, what's the purpose? The purpose is learning something new. And if you ever come across it someday, you're reading a paper and you read something about BCC and FCC structures and HKs and Ls, and you see some graph somewhere, it's going to mean something to you. And you might not remember it all, but again, you can go back and you can say, I know that I know something, and there's at least a starting point for you. All right, so depending on the exact method you use, and there's a lot of things you can do with X-rays, and depending on how you do it, you get different information out of it. You can even get the chemical makeup out of using X-rays and a crystal to try to see what the actual elements are that make up the material. And if you do that, so here's a quick picture. I have, let's say, a specimen here. I'm going to shoot in my my X-ray. There's going to be some angle that it comes in. There's going to be some angle that it comes out. There's a detector here. In this case, what it is, it's actually a powder, this crystal down here. So let's see if I can write that. I'm just going to write powder. We powderize our crystal and we rotate it. It's spinning. That way we get it at a lot of different angles. We can measure the whole thing. And what we're going to do is we're going to change this angle, and we're going to see where we have intensities at, where we have a lot of intensity happening as we take measurements. And when we do this, we just have I for intensity on this axis. Sometimes it's called counts. So how much intensity or how many counts we have, our detector saying that we have a hit. And over here, we're going to have on this axis, this is our 2 theta axis. We have 2 theta because we're using our 2 thetas that we have here. And what it's going to do is it's going to be kind of low. We're going to have a little bit of noise here and there. And then every once in a while, we're going to have a spike. And we will get something along the lines of this. And depending on where those spikes are at, we can know more about the material. We can know what chemical makeup the material has, and we have a lot of information that we can determine from it. So a lot of information. The main things that we're going to really focus on, that I really want you to focus on, is going to be these closed packed planes. I really want you to be able to visualize what's happening with the crystal. I want you to be able to visualize these planes so that we can know kind of that microstructure, or even smaller than what's normally considered the microstructure. We want to know what's happening with these bonds and these atoms. That's the main thing. Just as a side note, maybe lighten things up a little bit, we have these tessellation patterns. Some artists, they come up with these sometimes. Escher came up with them. Came up with a lot of them, and what they are is they're repeating patterns, and this is just a 2-dimensional representation basically of a unit cell. If we wanted to, we could say, all right, what is the smallest area that has a repeating pattern in it? And if we draw a box around it, or a circle or a triangle or whatever it happens to be, a circle wouldn't work, but if we draw something around it, some shape that can be repeated, I could then say we have the entire picture, and if I just keep repeating that over and over and over again, I get a bigger and bigger picture, but that picture never changes. It just gets bigger. The pattern never changes. So there's a couple of them here, and you can pause the video and you can try to figure out how that pattern repeats and where that the unit cell, that two-dimensional unit cell for these pieces of art or these patterns where it is.